how in the world do we get from A to B at the molecular level?
So here's the game plan. We're going to walk through this whole thing in 5 parts. We'll meet the molecules, see the key switch that makes it all happen, watch the atoms do their thing, then see how it's done in a real lab, and finally, how we prove we actually did it.
First up, let's introduce the stars of our show. Every great story needs its main characters.
Okay, so this is where it all begins. Aniline. It's our starting material, our foundation. I like to think of it as a block of marble, you know? It's got all the potential, we just need to shape it.
And this is our masterpiece, our finished sculpture, acetanilide. This is what we're aiming to create by carefully modifying that original aniline molecule.
Okay, now for the really cool part. What's the big idea here? How does this actually work? Well, it all comes down to a really clever and powerful chemical switch. The magic word for this whole process is acetylation. That's the key. It's kind of like we're doing a performance upgrade on our molecule. We're adding this new part, called an acetyl group, right onto the nitrogen atom of the aniline.
But you might be asking, where do we get this acetyl group? It doesn't just appear out of thin air, right? Nope. We need a delivery vehicle, and for that, we bring in our second ingredient, acetic anhydride. Think of it as the delivery truck carrying the exact part we need for the upgrade.
All right, let's zoom way in. Time to see what the atoms themselves are actually doing. It's like a carefully choreographed dance, and it happens in a few lightning-fast steps. So, the music starts with something called a nucleophilic attack. Sounds intense, right? But it's actually pretty simple. Think of it like magnets. An aniline's nitrogen atom is electron-rich. It's got some extra negative charge. Acetic anhydride has a carbon atom that's a little electron-poor, a bit positive. And you know what happens? Opposites attract. That magnetic pull is what kicks the whole thing off, bringing the two molecules together.
So that initial connection, that attack, sets off this super-fast chain reaction. You can see it here. First, a tiny hydrogen atom, a proton, just kind of shuffles over to a new spot. Then boom, a piece of the old acetic anhydride molecule gets kicked off. After one last little tweak, everything settles down, and we're left with our super-stable new molecule, acetanilide.
And this whole dance has a name, which actually makes a ton of sense. It's called an addition-elimination mechanism. Why? Because first we add the two molecules together, and then we eliminate a piece to get to the end. See? Pretty logical. Okay, so the theory is cool, but what does this look like in a real lab? Let's get out of the diagrams and into the flask. So here's how it goes down. You put your aniline in a flask, and then you start adding the acetic anhydride. But you do it slowly. You have to. This reaction gives off heat, it's exothermic, and you don't want it getting out of control. Give it a good stir for a few minutes, and the chemical transformation is happening right there in the flask.
And now for my favorite part, the big reveal. You take the whole reaction mixture and dump it into a beaker of ice-cold water. And bam! It's like instant crystallization. The sudden cold shock forces our new acetanilide, which isn't soluble in cold water, to crash out of the solution and form solid white crystals, right before your eyes. Then you just gotta filter them out.
Okay, so we've got our crystals, we're done, right? Not quite. There's one more step. We wash them with more cold water. Now, why would we do that? It seems a bit redundant, but trust me, it is super important for getting a pure product. Well, it's all about cleaning up the mess. See, the reaction creates some byproducts, mainly acetic acid. And that stuff loves water. So when we rinse our crystals with cold water, we're not dissolving our precious product. We're just washing away all those water-soluble impurities. It's like giving our crystals a final shower to get them squeaky clean. So we've made them, we've cleaned them. But in science, looks like is not good enough. You have to prove it. You need hard data to show that you made the right stuff.
For those who want exceptionally pure crystals, there's this really elegant technique called recrystallization. You dissolve your crude product in just enough hot water to get it all into solution. Then you let it cool down very, very slowly. As it cools, the acetanilide molecules find each other and arrange themselves into beautiful, perfect crystals, leaving all the junk behind in the water.
But after all that work, what's the final proof? The smoking gun? The one number that tells us, yes, you absolutely did it?
It's the melting point. It's that simple. Pure acetylenolide has a chemical signature. It melts right between 114 and 116 degrees Celsius. If your crystals melt cleanly within that tiny temperature window, you nailed it. That's your proof. It's like checking the ID of your molecule.
And that really gets to the heart of what science is all about, doesn't it? It's not just about the eureka moment of making something new. It's about the discipline and the rigor of proving that what you made is exactly what you think it is.
So, let me leave you with this. This whole process, this molecular dance of acetylation, it's not just some obscure thing you do in a chemistry lab. This exact same type of reaction is an absolute workhorse. It's used to make things you use every single day, stuff like common painkillers, dyes, even advanced polymers. The fundamental chemistry we just walked through, yeah, it's literally building the world around us.